Hypothalamus, artificial intelligence. Digital transformation powered by real-time autonomous and intelligent algorithms. Presents its solutions for decision-making, artificial intelligence, and disaster and emergency management. Disaster and emergency management implies framework. The challenge: develop a DSS for disaster and emergency management. The overall objective is to minimize potential negative economic impact and human life losses. The solution: design a set of mathematical models to address the problems arising from disaster management based on stochastic programming models. The benefit: a set of measures and mathematical models to prevent and/or reduce the impact of disasters, and it prepares the community to respond in the best way when a disaster strikes. The general approach of HI is to connect predictive and prescriptive analytics models, which implies an integrated holistic vision, multidimensional space-time, of the entire supply chain of disaster response services. Predictive analytics is based, mainly, in artificial intelligence, machine learning, and complex probabilistic methods. Prescriptive analytics in mathematical programming, better known as optimization. Activities to ensure safety. These mission areas may be grouped based on when a defensive action is intended to occur, either before, during, or after an attack. Proactive planning, mission areas whose defensive actions are taken before an attack occurs. These mission areas are prevention/protection, and mitigation. Real-time operational planning, mission areas whose required actions are taken during or immediately after an attack. These mission areas are detection and response. Recovery planning, mission areas whose required actions occur after an attack. This mission area is recovery. Natural disaster management. The mitigation and preparation of disasters caused by nature implies the overall objective is to minimize the potential economic and human loss, and continuity of operation of the economic system. To this end, the historical behavior of nature is studied, trying to know probabilistically what can happen in order to make decisions of where, when, and how to allocate resources to mitigate and/or prepare for the disaster. Actions before mitigation, set of measures to prevent or reduce the impact of disasters. Preparedness, preparing the community to best respond when disaster strikes. Given the uncertainty regarding disasters, the theory indicates that the only way to prepare for disaster is to probabilistically characterize risk, with predictive analytics, and based on that information to make optimal decisions on how to mitigate it, and how to prepare for it, using prescriptive analytics. The process involves making decisions in advance, regardless of any future scenarios, and simulating decisions for each of those scenarios. The decision should consider the expected value of the benefit, or the cost, and the control of extreme risks, which should not be assumed. The process of stochastic optimization involves 3 stages, 2 of predictive analytics. Stochastic process model converts historical data into a dynamic probabilistic model, and synthetic scenario generation turns the dynamic model into a synthetic scenario tree. When there is enough data, these 2 processes can be algorithmic, otherwise it is necessary to resort to a committee of experts. And 1 stage of prescriptive analytics. Stochastic optimization, it converts the scenario tree to here and now decisions, and with the simulated future decisions generates probabilistic distribution functions for the future. The model should include extreme risk control constraints. It is suggested to use the conditional value at risk as a risk indicator. In this case, the decisions to be implemented are associated with the optimal resource allocation policy for mitigation and preparation. Actions after reaction, the use of resources and emergency procedures to preserve the life, property, and environment of the community, since the disaster is occurring. Recovery, set of long-term actions to stabilize the community and return to normalcy. The reaction and recovery after the disaster occurs implies actions during the disaster, and reconstruction actions. Natural disaster management. It should be noted that each type of natural disaster has its own way of being faced, and of being mathematically modeled. Earthquakes, floods, tsunamis, Droughts,
huracanes,
tornadoes, forest fires. Cases, natural risk management. Case, earthquake management in Seattle. Decision support system for earthquakes management. Challenge, develop a decision support system for natural disaster management. The overall objective is to minimize potential negative economic impact and human life losses. Solution, design a set of mathematical models to address the problems arising from natural disaster management based on stochastic programming models. For this purpose, the historical behavior of nature is studied by trying to know probabilistically what can happen to make decisions where, when, and how to allocate resources to mitigate and/or prepare for disaster. Synthetic scenario generation models for each type of disaster should be generated by field experts in the field. Result, the implementation of the DSS for Seattle. Earthquake Management in Seattle. Pacific Rim Visualization and Analytics Center, PARVAC. It is made up of the following computer components. GOSR, Geospatial Optimization of Strategic Information and Resources. Platform of mathematical models and numerical algorithms for decision support and emergency management. JIC3, Just-in-Time Mobile Command and Control Environment. Command post for the deployment of personnel in emergency response, to optimize the flow of information about the emergency and response during an emergent event. RIMSIM, First Response Simulator for Common Pacific Rim Threats. Software based on a modular system, to simulate first response communications, common artifacts, and response actions in order to evaluate and improve the level of distributed knowledge, and VisSearch, Visual Search Aid System, by means of image or pattern detection strategies, and technological mediation. Decision support systems for disaster preparedness and response are challenging because uncertainty of events and difficulty obtaining real-time data. GOSR development optimization models for the location and allocation of medical supplies to be used in emergencies for the Seattle region. The distribution of supplies requires at least the decisions before the event, location of warehouses, and inventory levels of medical supplies after the disaster. Optimized allocation of medical supplies to hospitals to reduce delivery time. In the preparation stage, RIMSIM and GOSR integrate personnel training into a disaster command center. RIMSIM is used for simulation of the training environment, on the other hand GOSR is used for optimal decision making. In the response stage, GOSR is used for real-time transportation decision-making, while supply-demand information of the disaster is collected. The models to use previous to disaster are stochastic optimization model, selective warehouses, and determine inventory levels by balancing disaster risk, with on-time delivery of supplies. Transport model, transforms transfer orders into optimal vehicle assignment, and routing. In the response phase, the fundamental model is real-time optimization model. It results in the allocation and routing of vehicles, with up-to-date information on transport conditions, and current demand, and supply information. In this academic example, 2 Seattle earthquake scenarios were considered for the analysis: Seattle fault, M6,7 with probability 0.6, and Cascadia fault, M9,0, with probability 0.4. Additionally, it was considered 3 warehouses, 10 hospitals with demands of health services depending on the fault, 62 routes that connect warehouses with the hospitals, and 1 type of medical supply. The table presents the results obtained for the preparation stage, including inventory levels in each warehouse, expected quantities transported between warehouses and hospitals, and routes used. Inventory levels are decisions variables here and now, and they are independent of failure. Transport flows depend on each scenario, they are simulated variables. Case: earthquake management in Istanbul. Case: rebuilding New Orleans. Case: seismic risk management in Italian Tuscany. The document: Earthquake risk management via stochastic optimization, a case study for an Italian region. It describes how a stochastic spatial dynamic optimization model, which considers the complexities and interdependencies of catastrophic hazards, has been customized to explicitly incorporate the geological features of a region, the parameters of seismic hazards, and the vulnerability of the built environment. The model can analyze the interaction between investment and mitigation measures, and risk-sharing measures. Special attention is paid to the evaluation of a multi-pillar earthquake loss propagation program, involving the central government, and mandatory insurance. It is shown that the model can analyze multiple policy options, to develop insurance policy in an equitable and fair manner, and their effects on insurance premium and reserve funds. To analyze system stability, EASA uses a strong connection between non-differentiable stochastic optimization and risk measures such as value at risk and probability of insolvency. The study was developed for the Tuscany region. Even considering that Tuscany is not one of the most dangerous regions in terms of seismic activities, the case is quite representative for the methodological approach, since all the results have been normalized to refer to monetary units. The choice of Tuscany was determined because the Seismic Risk Research Institute of the Italian National Research Council had already made models and had data from a previous study. These data have been incorporated into a Monte Carlo generator of seismic events, which simulates the occurrence of earthquakes affecting the region, calculates the attenuation according to the geological characteristics, and finally determines the acceleration in the ground in each municipality. EASA's stochastic spatial dynamic optimization model has been customized to explicitly incorporate the vulnerability of the built environment, with data on the number and types of buildings in each municipality. In the first phase, the study has been limited to the study of different policy options for an insurance program. The next phase investigates the interaction between investments in physical mitigation, retroadaptation, and risk-sharing measures. Facility disasters. This methodology can be applied to the process of optimizing decisions to ensure shopping centers, housing developments, large-scale civil projects, or other facilities, whether it is from the point of view of the insurance company, maximizing profit and controlling the risk assumed, derived from the concentration, or from the customer's point of view, avoiding the concentration that could lead to the bankruptcy of an insurance company, that is, controlling the risk they assume. Mathematical modeling to reduce wildfire spread. The document Detecting critical nodes in forest landscape networks to reduce wildfire spread. It is the source of the information presented in this section. Mathematical modeling to reduce wildfire spread. Wildfires are an important ecological process in forested regions around the world, which can cause significant economic damage and often create widespread health impacts and environmental pollution. A network optimization approach to planning combustible material treatments in wildfires that minimize the risk of fire spread, in wooded landscapes below an upper limit for the total area treated. Simulation models are used to estimate the probability of fire spread between pairs of forest sites, and a critical node detection (CND) model is formulated that uses these estimated probabilities to find a pattern of combustible material reduction treatments that minimize the likely spread of fires through. Mathematical modeling controls the size and spatial contiguity of combustible material treatments. The authors demonstrate the approach with a case study in Kootenay National Park, British Columbia, Canada, where they investigated prescribed burning options to reduce the risk of wildfire spread. The results provide new insights into cost-effective planning to mitigate wildfire risk. The approach is applicable to other ecosystems with frequent wildfires, and to the design and redesign of industrial and/or environmental forests. Detection of critical nodes in a network of flammable forest sites. A forest zone can be thought of as a connected network of flammable areas, nodes, where connecting arcs, edges, represent possible vectors for the spread of fire between adjacent areas. To minimize the chance of fires spreading widely throughout the area, the administrator assigns a set of treatments, prescribed burns, between the nodes. Treating a node helps reduce the intensity of the fire for more effective suppression. For simplicity, it is assumed that treating a node is equivalent to removing the node and all arcs connected to that node from the forest network. It should be noted that treatments are not always completely effective. The administrator's problem is to determine the best way to divide the network to minimize the likelihood of fire spreading. A popular strategy to solve this problem is to reduce connectivity between nodes with flammable fuels in the forest area. This strategy can be implemented by solving a critical node detection (CND) problem, which finds critical nodes in a network whose removal degrades network connectivity to the maximum according to a chosen metric. The concept of critical nodes characterizes the vulnerability of a network after a portion of the nodes are removed, which, depending on the type of network, could be the result of natural disasters or technical failures. The CND problem has been applied in many disciplines, including security applications, transportation, social network analysis, and epidemiology. The images shows the following graphs. Graph A, a horizontal network of areas, graph, connected as a single component connected prior to interdiction. Graph B, an intercepted graph with two components connected. Large dots denote the deleted nodes, and Graph C, pairwise connections between nodes in the connected components after interdiction, dark blue lines. Case study. Kootenay National Park, British Columbia, Canada. The CND model was applied in Kootenay National Park in British Columbia, Canada. The maps show the location of Kootenay National Park and its main features. The park is part of a UNESCO World Heritage Site in the Canadian Rockies, and covers a subalpine and alpine region, with elevations between 1,200 and 3,400 meters above sea level. Forests at lower elevations in the area are dominated by Engelmann's fir, subalpine spruce, white spruce, and palo pine, and are replaced by alpine tundra at higher elevations. Lightning ignitions are a common cause of large fires. The Canadian Burn P3 model was applied to simulate ignitions and fire spread in the Vermilion Valley area, approximately 834 square kilometers, under the current management regime. The Burn P3 model generates stochastic fire ignitions and spread scenarios, which uses the Canadian Fire Behavior Prediction System (FBP) canopy fire scheme, modeling surface fires as well as the transition to canopy fires, and the rate of canopy fire spread. For each iteration, Burn P3 generates the ignition locations and perimeters of the individual fires. The Reimer et al. Fire regime is used, which assumes that fire management teams attack all fires detected in the area but, on average, 13% of ignited fires would escape the initial attack. Fire suppression has the greatest impact on fires that are small at the time of discovery and is substantially less effective when fires are already large. For example, Alberta reported 83% success in containing fires smaller than 3 hectares, and British Columbia reported 92% success in containing fires smaller than 4 hectares. A 5-kilometer buffer was added to allow fires to spread in and out of the study area. We calibrated the model to align generally with the historical fire size distribution in the Vermilion Valley area from the Canadian National Fire Database. The terrain network, G, includes 834 hexagonal nodes of 1 km2, interconnected in a triangular pattern. The size of the nodes must balance the numerical complexity of the problem, with its practical usefulness for real planning. It is an appropriate size to capture the patterns of natural fire barriers, such as individual mountain ridges, or rock outcrops, which have proven to be effective barriers to fire spread in the park, at a scale of 250 meters, and greater. Based on this fixed node size, the limit of treatment area, B, defined the number of nodes that would be removed from the network. The optimization model can be applied to evaluate two different scenarios. Probabilistic uses the unchanged probability values Pij to scale the Uij decision variables in the target function. In this scenario, Ij node pairs exhibiting the highest fire propagation frequencies have the greatest impact on the target value. These frequencies depend on the size distribution of the fires that ignite at node I and propagate to J, since fires started at I must be at least as large as the distance between I and J. In a forest landscape, the distribution of fire size follows a general function of the power law. Consequently, this scenario tends to be intersected by geographically distinct hot spots with small but frequent fires throughout the landscape, and binary. The values of Pij and the target function are replaced with binary fire propagation indicators, Pij bin, which are equal to 1 for Pij greater than 0 and 0 for Pij equals 0. Therefore, the scenario assumes equal unary weights for all node pair connections with Pij greater than 0. For each node I, the sum of the values of the bin Pij defines the possible extent of propagation of fires started in I, a fire basin area that the scenario minimizes. For a typical gridded network of forest sites, the number of connections between pairs of nodes grows in quadratic proportion to the linear size of a connected component, and thus the distance between a pair of nodes I and j grows. Consequently, the binary fire basin scenario minimizes the number of long paths between pairs of nodes and thus minimizes the spread of large fires. The probabilistic and binary forest scenarios can be viewed as alternative strategies for minimizing potential fire spread. Maps of optimal node removal solutions. Key fire regime metrics. Graph A, burn probabilities. Graph B, fire spread probabilities between node pairs, Pij, spread probabilities along network edges E between adjacent nodes are not shown, and Graph C, fire spread probabilities between adjacent nodes, Wij. The results of node removal solutions, based on land cover configuration, are presented in columns for 3 values of B, equal to 10, 20, and 30 nodes. Each column has 3 rows of maps for 3 variables for scenario 1. The panels of D through L show solutions, which ignored spatial contiguity constraints for site treatments, for treatment area, node removal. The solutions without fire spread information, D to F, split the central Vermilion Valley almost in half, while the rest of the budget was spent on isolating small valleys connected to the central valley by narrow corridors. As the treatment area limit B increased, a larger share of the budget was spent on isolating these small valleys. Incorporating information about fire spread changed the optimal node removal patterns. In the binary solutions, G to I, the central Vermilion Valley was not cut in half. Instead, the immediate focus at lower budget levels was on isolating the smaller valleys. As the treatment area increased, the model fragmented the area with high risk of ignitions in the southern part of the Vermilion Valley. The probabilistic solutions of the fire basin differed from the binary solutions of the fire basin, J to L. Most of the budget was spent on the partition of the area with an elevated risk of ignitions in the southern region. At the larger treatment area level, a small portion of the budget was allocated to the creation of 1, or 2, large divisions in the north. Compared to binary fire basin scenarios, no budget was spent on disrupting the narrow corridors connecting smaller valleys. In general, probabilistic scenarios more effectively reduce the local spread of fires between adjacent nodes than binary scenarios. Climate risk management. Case, sowing planning. One of the important risks, in which all companies are involved, is associated production processes in the bio-industrial sector, which are seriously affected by hydroclimatic conditions, whose volatility is increasing because of the global warming that is occurring on our planet. This situation means that the risks associated with the industries, whose financial statements depend largely on the climate, must be assessed and managed. The biggest problem for companies in the sector is that they must intervene in the process of sowing and harvesting bio-industrial products, since the management carried out by the operator derives the risk that a third company may end up assuming. Ignoring this situation can lead to a significant reduction in economic benefit, for a private company or a state-owned enterprise. In addition, the high geospatial correlation of climate must be considered, which increases risks, and the concentration of risks in a region, or in a type of product, must be carefully considered. Digital industrial revolutions. Industry 4.0 is a consequence of the invention of the digital computer and digital automation. Its origin may be in 2011, and the result is digitalization and interconnectivity, smart factories, that is, cyber-physical systems. Industry 5.0, the first mentions date back to 2015, is humanization and close collaboration between people and cyber-physical cognitive robots based on artificial intelligence. The transition from Industry 4.0 to Industry 5.0 represents a paradigm shift, we move from an approach focused exclusively on technological efficiency to one that prioritizes human value, sustainability, and resilience. While Industry 4.0 sought to interconnect machines so that they could make autonomous decisions, Industry 5.0 seeks to make these machines work with people to enhance their creativity and well-being. Formally introduced by the European Commission in 2021, this revolution does not replace the previous one, but complements it under three fundamental concepts. Human centrism: technology should serve people, not the other way around. It focuses on improving the health, safety, and job satisfaction of workers. Sustainability prioritizes circular processes that reuse resources, reduce environmental impact, and respect the planet's limits. And resilience, the industry's ability to withstand and adapt quickly to global crises, such as pandemics or supply chain disruptions. Industry 6.0 currently has no date, as it is considered a visionary and conceptual phase that is still being defined, but which is based on intensive artificial intelligence. Total autonomy, biological symbiosis, and industrial systems that function as living organisms. There are already examples of this situation, as is the case with smart grids and the Internet of Energy. Industry 6.0 focuses on the total symbiosis between humans, machines, and biological systems to create living, regenerative, and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. The fundamental pillars are: integration of mathematics and artificial intelligence, to produce artificial general intelligence, AGI, with the ability to understand, learn, and apply knowledge in any intellectual task, in the same way, or even better than a human being. Human-machine biology symbiosis, fusion of human intuition, advanced artificial intelligence, and biological systems, such as self-healing materials or neurocognitive interfaces. Cognitive and proactive autonomy, transition from predictive maintenance to self-regulation and regeneration. Systems not only detect faults but are reconfigured to avoid them altogether. Regenerative sustainability, beyond reducing environmental damage, systems are designed to actively restore and enhance ecosystems through real-time circular economies. And ethical and conscious governance, AI incorporates moral reasoning and transparency, ensuring that autonomous decisions are aligned with human values and planetary well-being. The technologies related to Industry 6.0 are: mathematical modeling, translation of real-world problems into a mathematical language, such as formulas, equations, or graphs, to understand, analyze, and predict behaviors of complex systems. Generative AI and AGI, co-creation of workflows and autonomous design of products based on abstract objectives. Quantum computing, massive data processing for optimization of ultra-complex supply chains and molecular simulations. Human digital twins, HDT, virtual replicas that simulate not only physical processes, but also emotional and cognitive dynamics of workers. Internet of Everything, I/O, and 6G, ubiquitous and ultra-low latency connectivity that enables the orchestration of swarms of cognitive robots and devices on a global and even spatial scale. There are 3 eras of modern mathematics aimed at handling computers. During this period, the basic mathematics that supports optimization does not change, but the technologies do. The creation of digital computers and iterative algorithms took place during Industry 3.0, in 1947. Until the arrival of Industry 4.0, the mathematics of algorithms grew, but it was from that moment that the complexity of formulations, and the use of solutions based on advanced technologies for large-scale optimization, generated the boom of modeling. This era includes Industry 5.0. The Industry 6.0 changes the mathematical modeling, giving rise to the orchestration of swarms of cognitive robots, and living industrial ecosystems. Industry 6.0 focuses on the symbiosis between humans, machines, and biological systems to create living, regenerative, and deeply ethical industrial ecosystems. Unlike its predecessors, it does not seek only efficiency or collaboration, but an integration where technology self-organizes and evolves along with society. Industry 6.0 is changing the mathematical modeling. Now we can talk about living industrial ecosystems, and orchestration of swarms of cognitive robots. This has led to the fact that, if desired, modeling in Industry 6.0 is autonomous, without human participation or coordination problems. One of the most impactful changes occurs with the arrival of the Internet of Things, IoT, which began to change the models that ran at discrete frequencies, such as days, weeks, months, for real-time models. It can be said that in Industry 6.0 all models work in real time, so that the world reacts distributed and online, for all IoT connected systems. For static systems, the methodology is also valid, but the world is dynamic. IoT is fundamental in environmental monitoring and disaster risk management. It uses satellite systems, regional networks of HD cameras, radars, and autonomous drones, for the early warning of natural disasters through intelligent image analysis. HI has developed artificial brains to address the problem. The interrelationship between the different types of disasters requires that, to carry out the best possible management, which minimizes casualties and economic costs, it is necessary to have a holistic view of the whole problem. Unfortunately, the mathematical models needed for each type of disaster are different. Industry 6.0 implies a very different view of the problem than Industry 4.0. Industry 6.0. A swarm of artificial intelligence algorithms, that is the orchestration of swarms of cognitive robots on a global scale. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. The swarm of algorithms make up an artificial brain that can be solved using Industry 4.0 or Industry 6.0 models. The latter seems to be the right thing to do. Living industrial ecosystems that act autonomously, making their own decisions, and reaching agreements with other living industrial ecosystems, to ensure the optimality of the living industrial ecosystems network. For real-time optimization purposes, the artificial brain does not need a coordinator model. Each disaster site has an associated model that acts autonomously and independently. The Industry 6.0 artificial brain does not require a human supervisor. In the case of disaster planning, there may be multiple disaster locations, in which certain types of disasters may occur simultaneously. The coordination of all the models is carried out by a consensus algorithm based on the duality theory. Consensus algorithms are fundamental to the operation of decentralized networks. They ensure that all network participants agree on the validity of transactions. Without consensus, there would be discrepancies in the data between different nodes, which could lead to fraud and errors. These algorithms facilitate trust between users who may not know or trust each other. Different consensus mechanisms have been developed to respond to the needs of various applications, each with its own strengths and weaknesses. In the case of mathematical programming, the rules of consensus are exact. MOS, Natural Disaster, Planning and Control Center. The regional IoT combines local data processing, through edge computing, with IoT connectivity to process high-definition video and image streams, in specific geographical areas. This technological convergence allows intelligent analysis in real time, directly where the data is generated, without depending on a centralized infrastructure in the cloud. Specialized AI algorithms in deep learning are used in tasks such as pattern recognition, anomaly detection, and predictive activities at the source site. Mathematical models as a service on the cloud. This facilitates access to enterprise-wide optimization systems and artificial brains developed by HI, a service for companies undergoing digital transformation, Value Chain Optimization. MOS is an Advanced Decision Support System, DSS, made up of multiple mathematical models, predictive and prescriptive analytics. These models are the same as those used by large companies, the big difference is their cost of access. MOS socializes current analytical technologies, mainly those related to artificial intelligence, machine learning and mathematical programming. In this way, companies increase their value by fully entering the new world generated by the digital transformation of Industry 4.0. Why MOS? Because a single instance of the mathematical model is useful for several users. Installing the software locally is a thing of the past, plus MOS provides a way to aggregate, collect, and centralize valuable application data. In MOS, the cost of developing a complex mathematical model is paid by several users. The alternative that is replaced is that a single user pays only for the mathematical model. What is MOS for? In addition, in the past there was a constant problem for large and medium-sized companies related to the amount of mathematical modeling software they had to acquire to support different types of decisions within their organizations. All this meant buying optimization software, basic algorithms for solving numerical problems and mathematical models that represent real-life problems, i.e., paying for specialized software licenses, high-performance computers to solve math problems, and servers suitable for interconnecting different users within a company. In MOS, mathematical models are provided as a service over the internet in a centralized manner. Users have to create individual accounts and all costs generated are billed daily, weekly, monthly or annually, depending on the options and the decision of who contracts the service. The algorithms associated with the mathematical models run online on a high-performance computer in the cloud. The current state involves the integration of edge computing and cloud computing to implement an enterprise-wide optimization system composed of multiple highly complex mathematical models. The integrated model, an artificial brain produced by HI, can be distributed across various types of computers. Artificial brains are backed by the technological power of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, made up of bit supercomputers, and the birth of quantum computers, and their commercialization process, which will be by runs of applications, which will be solved in the blink of an eye. As a standard configuration, HI proposes to use a CPU-S cluster with many GPUs. This implies that applications are deployed using intelligent devices based on the symmetrical atomization of systems and/or processes. As is the case with GPT-based artificial intelligence. The computational support of a large company will integrate multiple types of specialized servers, all of them supplied by third parties, which must guarantee their correct operation. This central computing system will be accessed by users of companies that use MOS, working in an external logical network. The company's data and application servers will be located at this same layer. Artificial brains are backed by the technological power of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, made up of bit supercomputers, and the birth of quantum computers, and their commercialization process, which will be by runs of applications, which will be solved in the blink of an eye. As we have seen, there are multiple architectures that a company can implement to meet its needs. The economic implications vary with the user's decisions and needs. At this level of the proposal, the following configuration has been assumed. In the cloud, optimization server provides compute time hosting, optimization platform licenses, and mathematical model licenses. Optimization database, temporary files used by high mathematical models. On the client, company database, permanent files used by the company, and potentially read by HI's mathematical models. Business user, cloud optimization system access workstations. GAMs provide the optimization services in the cloud. One of the great advantages of MOS is that the user can be an SME, small and medium-sized company that would otherwise not be able to access advanced artificial intelligence. The image presents the components that have to do directly with optimization, whose capacity must be designed, and that generate costs that the user must assume. The first element to consider is the multi-core and multi-threaded CPU, its architecture, and the software components it stores, which are presented below. Anticipation. It is the core of decision-making under Environment 4.0. It is not a question of reconstructing the damage caused by a disaster, with decisions a posteriori. It is about anticipating and mitigating with actions before the disaster. And the best way to do that is to use the mathematical modeling power under the new technological paradigm. The enchanting charms of this sublime science, mathematics, reveal only to those who have the courage to go deeply into it. Carl Friedrich Gauss. Thank you for your attention.